This question is about hydrocarbons. Ecocene C20H42 can be cracked by heating to 700 Kelvin in the presence of a catalyst. The products are an aromatic hydrocarbon, an alkane and another alkane. So we're looking to count up what we've got left. So we've got, in terms of the carbons, we started off with 20 and we subtracted 8 and we subtracted 6. So at 20 take away 8 take away 6 leaves us with 6. We had 42 hydrogens and we subtracted 10 and we subtracted 14. So we had 42, subtract 10, subtract 14. We've got 18 left. Now, an alkane has to go CnH2n plus 2. So if it was 6, it would need to be 14, which doesn't work. 6 could be 2 3s. If it was 2 3s, it'd be 3 and 8. And 8 times 2 is 16. So it's getting closer, but it still doesn't work. So if it was 2s, C2H6, if we have 3 of those, we will have 6 Cs and 18 H's. So it must be 3 ethanes. It says, give a suitable catalyst for this reaction. So there's a number of answers that you can give, but the one that I like to give straight from the specification is zeolite. When I'm teaching my students about cracking, we've got thermal cracking at a high temperature and a high pressure, and catalytic cracking at high temperature, a slight pressure, and in the presence of a zeolite catalyst. And if you say that high slight zeolite, it might help you remember because it kind of rhymes. Catalytic cracking, high slight zeolite. Figure 2 shows the carbon-13 spectra for an aromatic hydrocarbon C8H10. I've brought in table C from the data sheet so that we can see it. What we can see here is that we've got 1, 2, 3, 4 peaks in this region, 110 to 160. So we've got 4 benzene carbons and 1 other this type of carbon. So 4 benzene. So 5 peaks altogether, so only 5 types of carbon, 4 benzene types, and then 1 CC type. And the question says, which of these is the structure? So we're just going to have to work through them. So if we have a look at the first one, we can see that the first one is symmetrical both about this point and this point. It's a bit hard to see the structure when I do that, so I'm just going to remove those for a second, but you can see what I mean. So this A carbon is the same as this one, and this B is the same as this B here, because they're in this mirror plane. And then these C's are the same as each other because they're vertically mirrored, but they're the same as these two because they are mirrored in that horizontal mirror as well. So this would have only 3 peaks, so it's definitely not A. If we look at B, B is symmetrical about this point, so we've got 2 methyl groups the same, and we've got 2 attachment points the same, and then C on the mirror line and D on the mirror line, and then E here mirrored. These are so we've got 5 types, which is what we said, 5 peaks, of which 4 are benzene. So it looks like this is right, but we can check all the others. This one is mirrored here. So if these are my A and these are my B, these would be C and these would be D. So that's only 4 types, not 5. And then if I were to do D, it's symmetrical this way. So I've got 2 non-benzene type carbons here. Then I've got C, D, E and F, and that's giving me 6 types. So the answer was B. Cracking can also be done without a catalyst, high temperature, high pressure. State the type of product formed in a high percentage. So when you do thermal cracking, you get a high percentage of alkenes and some alkanes. So lots of alkenes for polymers and some alkanes for fuels. A sample of butane has volume 20 centimetres cubed, and it's burned in 1,350 centimetres cubed of air. The final mixture is cooled, so it's air. So the whole of this is 1,350 centimetres cubed of air. Calculate the total volume of gas in the final mixture. Assume that air is 21%, so 21%, 79% by volume oxygen. Okay, so if I were to start with 20 centimetres cubed of butane, I would need, times it by 6.5, I would need 130 centimetres cubed of oxygen, and I would make, we'd start with none of that, and I would make 20 times 4 is 80, and 20 times 5 is 100. But it says that they're cooled to room temperature, so this would be cooled and it would become a liquid. So that one wouldn't count. So I'd have 80 centimetres cubed of this. What I need to work out is how much oxygen I had initially, because I had 1,350 centimetres cubed of air. What amount of oxygen did I have initially? So 21 over 100, so 21%. So that's 283.5 centimetres cubed. So 283.5, and I used 130 of it. Okay, so that was the volume of oxygen initially. I'm going to subtract, so the not moles, the volume of O2 remaining equals 283.5 minus the 130 that we were going to use up, 153.5 centimetres cubed. So I've got this much oxygen remaining. Okay. We know that we made 80 centimetres cubed of CO2. But how much of the gas was left just from the air? So remembering that this was 283.5, what was the 79%? So you can either do 79% or subtract 283.5 from your 1,350. So we used up some of the oxygen. What we need to do now is add on, so the volume of air, not oxygen, is 79% of 1,350. That was our 1,066.5. So I now need to add up these three numbers to get the total. So add on 153.5 and add on 80, and I'm getting 1,300 centimetres cubed. So we've got the unreacted oxygen, the formed CO2, and the part of the air that wasn't oxygen in the first place. Natural gas is used in power stations to produce electricity. It contains sulfur impurities. Sulfur dioxide forms when these impurities burn. What's the environmental problem? Well, sulfur dioxide reacts with water to form sulfuric 4 acid, which is a component of acid rain. And what could be used to remove these? So you might have learned about this in your Group 2 studies. So either calcium oxide or calcium carbonate react with these to make calcium sulfate 4, removes it from flue gases.